In this lecture, we will discuss the naive Bayes classifier. After this video, you will be able to discuss how a naive Bayes model works for classification, define the components of Bayes' rule, and explain what the naive means in naive Bayes. A naive Bayes classification model uses a probabilistic approach to classification. What this means is that the relationships between the input features and the class is expressed as probabilities. So given the input features for a sample, the probability for each class is estimated. The class with the highest probability then determines the label for the sample. In addition to using a probabilistic framework for classification, the naive Bayes classifier also uses what is known as Bayes' theorem. The application of Bayes' theorem makes estimating the probabilities easier. In addition, naive Bayes assumes that the input features are statistically independent of one another. This means that for a given class, the value of one feature does not affect the value of any other feature. This independence assumption is an oversimplified one that does not always hold true, and so is considered a naive assumption. The naive independence assumption and the use of Bayes' theorem gives this classification model its name. We will cover Bayes' theorem and the independence assumption in more detail in this lecture. Before we look at naive Bayes in more detail, let's first start with some background on probability. Probability is the measure of how likely an event is. The probability of an event A occurring is denoted P and in parentheses A. It is calculated by dividing the number of ways event A can occur by the total number of possible outcomes. For example, what is the probability of rolling a die and getting 6? When you roll a die, you can get a number from 1 to 6, so the number of possible outcomes is 6. The number of ways for getting 6 is 1, since the way you can get 6 is if the die shows 6 when it stops rolling. That means that the probability of getting the number 6 when you roll a die is 1 over 6. This is denoted P of 6, and that's equal to 1 over 6, and is read as the probability of 6 is 1 over 6. There's also joint probability. The joint probability specifies the probability of event A and event B occurring together. In this diagram, the probability of event A occurring is shown as the blue circle, and the probability of event B occurring is shown as the green circle. Then the joint probability, that is, the probability of A and B occurring together, is shown as the overlap of these two circles. The joint probability of A and B is denoted P and in parentheses A, B. For an example of joint probability, let's consider rolling 2 dice together. What is the probability of getting 2 6s, or a 6 from each die? If the two events are independent, then the joint probability is simply the result of multiplying the probabilities of the individual events together. In this case, then, we have the probability of rolling a 6 for each die is 1 over 6, so the joint probability is 1 over 36. This leads us to conditional probability. The conditional probability is the probability of event A occurring given that event B has already occurred. Another way to say this is that event A is conditioned on event B. The conditional probability is denoted P and in parentheses A, vertical line B, and is read as probability of A given B. This diagram gives a graphical definition of conditional probability. As before, the blue circle is the probability of event A occurring. The green circle is the probability of event B occurring. The overlap is the joint probability of A and B. The conditional probability P of A given B then is calculated as the joint probability divided by the probability of B. The conditional probability is an important concept in classification, as we will see later. It provides the means to specify the probability of a class label given the input values. The relationship between conditional probabilities P of B given A and P of A given B can be expressed through Bayes' theorem. This theorem is named after a reverend named Thomas Bayes who lived in the 1700s. It is a way to look at how the probability of a hypothesis is affected by new evidence gathered from data. Bayes' theorem expresses the relationship between probability of B given A and probability of A given B as shown in this equation. Bayes' theorem is also known as Bayes' rule or Bayes' law. Now that we have reviewed some background on probability, let's see how all this relates to the classification problem. With the probabilistic framework, the classification task is defined as follows. Capital X is the set of values for the input features in the sample. Given a sample with features X, predict the corresponding class C. Another way to state this is, what is the class label associated with the feature vector X? Or, how should the feature vector X be classified? To find the class label C, we need to calculate the conditional probability of class C given X for all classes and select the class with the highest probability. So for classification, we want to find the value of C that maximizes the probability of C given X. The problem is that it is difficult to estimate this probability because we would need to enumerate every possible combination of feature values and to know the conditional probability for each class given every possible feature combination. And here's where Bayes' theorem comes into play. The classification problem can be reformulated using Bayes' theorem to simplify the classification problem. Specifically, using Bayes' theorem, probability of C given X can be expressed using other probability quantities which can be estimated from the data. Here is Bayes' theorem again, with some additional terms defined. Probability of C given X is referred to as the posterior probability, since it is the probability of the class label being C after observing input features X. Probability of X given C is the probability of observing input features X, given that C is the class label. This is the class conditional probability since it is conditioned on the class. Probability of C is the probability of the class label being C. This is the probability of each class prior to observing any input data, and so is referred to as the prior probability. The probability of X is the probability of observing input features X, regardless of what the class label is. So for classification, we want to calculate the posterior probability P of C given X for each class C. From Bayes' theorem, probability of C given X is related to probability of X given C, probability of C, and probability of X. Probability of X does not depend on the class C. Therefore, it is a constant value given the input X. Since it is the same value for all classes, the probability of X can be removed from the calculation of probability of C given X. What's left then are the probability of X given C and the probability of C. So estimating the probability of C given X boils down to estimating the probability of X given C and probability of C. The nice thing is that probability of X given C and probability of C can be estimated from the data. So now we have a way to calculate probability of C given X, which is what we need for classification. To estimate the probability of C, which is the probability that the class is C before observing any input data, we simply calculate the fraction of samples with that class label, C, in the training data. For this example, there are 4 samples labeled as green circles out of 10 samples. So probability of green circle is 4 out of 10, or 0.4. Similarly, the fraction of samples labeled as red triangles is 6 out of 10, or 0.6. So estimating the prior probabilities is a simple count of number of samples with each class label, divided by the total number of samples in the training data set. In estimating probability of x given c, which is the probability of observing feature vector x, given that the class is c, we can use the independence assumption to simplify the problem. The independence assumption of the naive Bayes classifier assumes that each feature x sub I in the feature vector x is conditionally independent of every other feature given the class C. This means that we only need to estimate the probability of x sub I given C instead of having to estimate the probability of the entire feature x given C for every combination of values for the features in X. Then we would simply multiply these individual probabilities together to get the probability of the entire feature vector X given the class C. To estimate the probability of x sub I given C, we count up the number of times a particular input value is observed for the class C in the training data. For example, the number of times that we see the value of yes for the feature homeowner when the class label is no is 3, as indicated by the green arrows. This is divided by the number of samples with no as the class label, which is 7. This fraction, 3 out of 7, is the probability that homeowner is yes, given that the class is no. Similarly, the samples with the value of single for the feature marital status when the class is yes are indicated by the red arrows. And the probability that marital status is single, given that the class label is yes, is 2 out of 3, or 0.67. Some things to note about the naive Bayes classification model are: it is a fast and simple algorithm. The algorithm boils down to calculating counts for probabilities and performing some multiplication. So it is very simple to implement, and the probabilities that are needed can be calculated with a single scan of the dataset and stored in a table. Iterative processing of the data is not necessary, as with many other machine learning algorithms. So model building and testing are both fast. It scales well. Due to the independence assumption, the probability for each feature can be independently estimated. This means that feature probabilities can be calculated in parallel. This also means that the dataset size does not have to grow exponentially with the number of features. This avoids the many problems associated with the curse of dimensionality. This also means that you do not need a lot of data to build the model. The number of parameters scales linearly with the number of features. The independence assumption does not hold true in many cases. In practice, however, the naive Bayes classifier still tends to perform very well. This is because even though naive Bayes may not provide good estimates of the correct class probabilities, as long as the correct class is more probable than any other class, the correct classification results will be reached. The independence assumption also prevents the naive Bayes classifier to model interactions between features, which limits its classification power. So the increased risk of smoking and a history of cancer would not be captured, for example. The naive Bayes classifier has been applied to many real-world problems, including spam filtering, document classification, and sentiment analysis. To summarize, the naive Bayes classifier uses a probabilistic framework for classification. It applies Bayes' theorem and the feature independence assumption to simplify the problem of estimating probabilities for the classification task.